Hi everyone. Welcome to Chapter 2 to 2D Drawing Representation. In this chapter, we'll explore one of the most essential foundations in engineering graphics, how we represent three-dimensional objects accurately in two-dimensional space. Whether you're designing a mechanical part, a packaging component, or a structural system, the ability to create clear and standardized 2D technical drawings is a vital communication tool in engineering, design, and manufacturing. Throughout this chapter, we will be covering several important subtopics. First, we'll look into the principles of graphical projection, where we learn how a 3D object can be visually translated onto a flat surface. Then, we'll move into projection theory, which helps us understand how visual rays, projection lines, and planes work together to form views. We'll also explore the methods of projection, including both parallel and perspective projections, and how they differ in usage and accuracy. From there, we'll go deeper into parallel projection, focusing on orthographic projection, which is the standard method used in engineering drawings. Under this, we will discuss both multiview drawings, where different sides of the object are shown separately, and axonometric drawings, which allow for a more pictorial representation without distortion. Next, we'll discuss drawing standards, which ensure consistency across technical drawings. This includes understanding sheet sizes, drawing scales, and the types of lines used to represent different features like visible edges, hidden parts, centers, and section cuts. We'll also cover dimensioning guidelines, which teach you how to correctly place and format measurements on your drawings to clearly communicate the size and position of every feature. Finally, we'll examine the ANSI technical drawing views, where you'll learn about specific view types such as model views, section views, broken views, detail views, and exploded views, all used to improve clarity and precision in representing complex parts and assemblies. To help you learn effectively, this chapter is divided into two lecture parts. Part 1 is titled Fundamentals of 2D Drawing and Projection. Here, we'll build your understanding of projection principles, theory, and the basic methods used to represent 3D shapes in 2D. Then, in Part 2, we will focus on the practical side, learning about drawing standards, how to apply dimensioning rules, and how to read or create ANSI-compliant drawing views. Let's now proceed into the first part of our lecture, where we'll explore the fundamentals of 2D drawing and projection, the core concepts that form the foundation of all technical drawings. By the end of this part, students should be able to explain and apply the basic principles of graphical projection to create accurate orthographic multiview and axonometric drawings of simple 3D objects. Let's take a moment to revisit what we've learned so far before moving on. On this slide, you can see how a real-life product, in this case, a plastic bottle, is represented using technical drawings. On the left, we have the actual product. On the right, we see multiple technical views of that same bottle, the front view, right view, top view, bottom view, and even an isometric view, which gives us a 3D-like representation. Each of these views is carefully constructed to show different sides of the object with accurate proportions and detail. This is the foundation of what technical drawing is all about, translating real-world objects into standardized 2D views that anyone in engineering, manufacturing, or design can interpret correctly. Now, what makes these drawings good? On the right-hand tag, we have summarized the key criteria. A good technical drawing must be accurate, shapes and sizes must match the real product. It must also be clear and easy to understand, especially for someone who didn't create the drawing. It should be complete, meaning all the necessary views, dimensions, and notes are present. It must follow established standards, like ANSI or ISO, so that there is consistency across the industry. Dimensioning is also critical. The numbers and units need to be properly placed and easy to read, with no duplication. And when it comes to scale, the drawing should reflect the actual size or a proportionally accurate version of it. Lastly, a good drawing uses the right line types, solid, dashed, center lines, etc., and it should be neat, organized, and professional in appearance. So when we move from a real-world product to a drawing, we aren't just sketching, we're communicating. And just like a good message, a good technical drawing must be precise, understandable, and complete. Now let's begin by understanding the principles of graphical projection. At the heart of technical drawing lies this very important idea: How do we take a 3D object and represent it clearly and accurately on a flat piece of paper or computer screen? That's where graphical projection comes in. Graphical projection is basically a method of flattening a 3D object onto a 2D surface so that we can communicate its shape, size, and structure without needing to calculate complex formulas. It's visual, and it's logical. Instead of imagining numbers, we use lines and views to represent the object from different angles. As you can see from the drawing in this slide, we have a 3D mechanical part. When we apply projection, we create 2D views that lay out the object's features in a clear and measurable way. This includes dimensions like radius, diameters, and linear lengths, all shown in accurate scale. The quote here puts it simply: an image of a 3D object is projected onto a planar surface without any numerical calculation. That means everything you see in a 2D technical drawing, front view, top view, side view, comes directly from this concept. Now that we've got a sense of what projection is, let's explore the two main building blocks of graphical projection: the projection line and the projection plane. First, the projection line, also called the projector or line of sight, is like an imaginary ray of light coming from your eye and hitting the object. These lines help us transfer a 3D shape from the real world onto a 2D surface. Depending on the method, these lines can either stay parallel, like rays of sunlight, or converge to a point, like looking down a hallway. On the other hand, the projection plane, also called the image plane or reference plane, is the surface where your 2D drawing appears. Think of it like a sheet of glass where the image is captured. This plane can be vertical, horizontal, or from the side, and these are what we call the frontal, horizontal, and profile planes. Each one gives us a different view of the object, front, top, or side. If you look at the bottom diagrams, you'll see the difference between parallel projection, where lines don't meet, and perspective projection, where lines meet at a point. That's the geometry behind everything we draw in technical drawing, and understanding this will help you see how a 3D shape becomes a set of 2D views on your paper. Let's take a deeper look into what perspective and parallel projection really are. Let's begin with perspective projection, shown on the left side of the slide. Perspective projection is what we typically see in real life and photographs. It mimics how the human eye sees. Lines converge at one or more vanishing points, giving depth and realism. You can see examples like 1-point, 2-point, and 3-point perspective. Notice how the objects appear smaller as they go further away. This is what gives that realistic look. However, because of this distortion, engineers don't usually use perspective drawings for manufacturing or technical communication. They're harder to draw accurately and can misrepresent the true size and shape of the object. They are more common in architecture or illustration when the goal is to create a realistic image. On the other hand, we have parallel projection, which is the preferred method in engineering. In this method, the projection lines don't meet at a point, they stay parallel. This means the object's size and proportions stay true, making it ideal for technical and manufacturing drawings. Within parallel projection, there are several subtypes, which are shown in the right half of the slide. We have oblique projection, where the front face is drawn in its true size, and depth is shown at an angle, usually 30 degrees or 45 degrees, giving a quick 3D look. It includes cabinet, cavalier, and military styles. Then we have orthographic projection, which is the backbone of technical drawing. It involves multiple 2D views, like front, top, and side, and includes multiview drawings. This method is precise and standardized. Lastly, there's axonometric projection, a type of orthographic projection where the object is rotated to show multiple sides at once in a single view, like isometric, dimetric, and trimetric projections. These are often used for instruction manuals or assembly guides where a clear 3D understanding is needed but without distortion. Now let's take a closer look at a specific type of parallel projection known as oblique projection. This is where we project the front face of the object in its true size and shape, just like an orthographic projection, but the depth is projected at an angle, usually 30 or 45 degrees. What makes oblique projection special is that while the lines used for depth are parallel, they are not perpendicular to the drawing plane. This gives a more pictorial view, which is useful for sketches and concept visuals. There are three common styles of oblique projection: cavalier, cabinet, and military. Each one treats the depth differently. In cavalier projection, the depth is shown at full scale, 100%, which can make the object look a bit stretched or too deep. It's usually used for quick technical sketches because it's fast to draw. In cabinet projection, the depth is scaled down, typically to 50%, making it look more realistic. This is more suitable for presentation drawings where appearance matters more than exact scale. Lastly, we have the military projection, which is a bit different. Here, the top view is shown in true shape and size, and the height of the object is projected upward at an angle, typically 45 degrees from the horizontal. It's commonly used in mapping, terrain studies, and military applications. So, while oblique projections aren't used for exact manufacturing or measurement, they're very handy for conceptual design, rough planning, and early-stage communication. Now let's move on to one of the most essential types of projection used in engineering and manufacturing, orthographic projection. This method is part of the parallel projection family, where the projection lines are perpendicular to the projection plane. That means there's no distortion. What you see on paper matches the real shape and size of the object. Orthographic projection works by projecting a 3D object onto several 2D planes, typically the front, top, and right side views. Each view is like looking straight at one face of the object. This allows designers, engineers, and manufacturers to understand the full shape and structure of a product with accuracy. Let's break this down further into two types of orthographic views, multiview and axonometric. In a multiview projection, the object is shown using several 2D views, with each view taken from a specific direction, usually the front view, top view, and right side view. These views are arranged carefully and aligned spatially, meaning the top view is directly above the front view, and the side view is placed appropriately next to it. This kind of layout is very standardized, following ANSI or ISO rules, so people anywhere in the world can understand the same drawing. Then we have axonometric projection, also called pictorial orthographic. This projection still uses parallel lines but presents the entire object in a single 3D-like view. This helps you visualize the form of the object more easily, even though it's not as precise for dimensioning. Axonometric includes isometric, dimetric, and trimetric types, depending on how the axes are angled. Let's focus more closely on multiview projection, which is the most widely used form of orthographic projection in technical drawing. This method is all about representing a 3D object through several flat, 2D views, typically the front, top, and right side views. Sometimes, if necessary, we also include the left, bottom, or rear views to fully describe the object. Each view in multiview projection only shows 2 dimensions at a time. For example, in the front view, we only see height and width. The depth is not visible there, it shows up in the side or top view. All the views are arranged carefully and aligned with each other, and most importantly, they're projected perpendicularly. This perpendicular alignment ensures we get the true shape and size of each face. As shown in the illustrations on the slide, the object is placed inside an imaginary box, and each face of the box gives us one view. Think of it like unfolding a cardboard box where each side becomes one drawing view. You can see this in the top right image, where the object is surrounded by labeled planes, top, front, right, and so on. One thing to note is that multiview projections do not have distortion. The lines of sight are straight and orthogonal, at 90 degrees, which makes them extremely precise, ideal for manufacturing, dimensioning, and CAD modeling. That's why engineering blueprints and production drawings, whether done by hand or with software, follow either ISO or ANSI multiview standards. Multiview projection uses 2D views, typically the front, top, and side views, to accurately represent the shape and dimensions of a 3D object. Instead of showing all sides at once like a pictorial drawing, multiview separates each face into a distinct view, projected onto different planes. This allows engineers, designers, and manufacturers to measure and interpret the object with high precision. There are 2 major standardized systems for arranging these 2D views on a technical drawing sheet, which are first-angle projection and third-angle projection. These systems differ in how the views are positioned relative to the front view, and they are guided by regional standards such as ISO, for first angle, used in Europe, and ANSI, for third angle, used in the US and Malaysia. Understanding which system is being used is crucial to avoid misreading the drawing, especially in global or collaborative design environments. Let's start with the first angle projection shown on the left. In this system, the object is imagined to be in the first quadrant, meaning the object lies between the observer and the projection plane. Here, the projection plane is assumed to be opaque. When you unfold the views, the top view is drawn below the front view, and the right side view is drawn to the left of the front view. This method is commonly used in European countries and follows ISO standards. Now on the right side, we have third-angle projection, which is more common in Malaysia, the United States, and Canada, and follows the ANSI standard. In this method, the object is placed in the third quadrant, meaning the projection plane lies between the observer and the object. The plane is assumed to be transparent, like a glass sheet. So when you unfold the views, the top view appears above the front view, while the right side view appears to the right of the front view. You will also notice the symbols used to identify each system. These icons must be included on engineering drawings to avoid confusion, especially if they're being shared internationally. This slide provides a clear side-by-side comparison between first-angle and third-angle projection, the two main standards for arranging orthographic views in multiview drawings. These systems are fundamental in technical drawing because they affect how viewers interpret the spatial arrangement of the object being represented. On the left, we see the first-angle projection. In this method, the object is imagined to be placed in the first quadrant, meaning the object is located between the observer and the projection plane. As a result, views are projected through the object onto the planes behind it. The top view is placed below the front view, and the right side view is placed on the left of the front view. This arrangement can feel counterintuitive for those used to reading drawings from regions that use third-angle projection. On the right, the slide illustrates third-angle projection. Here, the object is imagined to be in the third quadrant, so the projection plane lies between the object and the observer. The views are projected directly onto the paper or screen. This results in a more intuitive arrangement. The top view is above the front view, and the right side view is on the right, matching the object's actual orientation in space. This slide presents a clear and structured example of multiview projection. It demonstrates how a complex 3D object can be precisely described using multiple 2D views, namely, the top view, front view, and right side view, which are each projected perpendicularly from the object. Additionally, an isometric view is included to help visualize the overall 3D form of the part more intuitively. The isometric view, placed at the top right, offers a pictorial representation of the object. Unlike the orthographic views, it shows height, width, and depth simultaneously, giving a more realistic and complete look at the shape. However, it's important to note that this view does not maintain true scale or exact angles. It's meant for visualization, not measurement. To the left of the isometric, the top view reveals the object's layout as seen from above. It displays the width and depth of the part, making features like the circular hole and rounded edge easy to identify. Below it, the front view is the most descriptive, showing the part's overall height and width. This view also includes essential information like the step profile and the vertical placement of the hole. Meanwhile, the right side view, located on the bottom right, complements the front view by providing details about the object's depth, information that isn't visible from the front or top. These three views are spatially interrelated, meaning they are aligned and connected in space based on a consistent and logical layout. This alignment allows each view to correspond accurately with the others, making it easier to interpret the 3D geometry of the object. The red dashed line illustrates how specific features align between the front view and the top view. For instance, a hole or edge seen in the front view appears directly below its corresponding feature in the top view. Similarly, the green dashed line shows the alignment between the front view and the right side view, ensuring consistent height and vertical dimensions across the projections. Let's move on to the concept of axonometric projection. Unlike multiview projections, which separate an object into multiple 2D views, axonometric projections display a 3D object in a single view while preserving the true dimensions and proportions. This type of projection is especially useful for visualizing the overall shape and structure of a component without distorting its measurements, as seen in perspective drawing. Axonometric projection is divided into three main types: isometric, dimetric, and trimetric. These classifications are based on the angles between the projection axes and the varying degrees of foreshortening applied to each axis. In isometric projection, all three axes are equally inclined at 120 degrees to each other. This results in all three dimensions, height, width, and depth, being foreshortened equally. It is the most commonly used axonometric projection in engineering and CAD because it is simple to construct and interpret, while maintaining dimensional accuracy. Dimetric projection, on the other hand, involves two axes that share the same angle and level of foreshortening, while the third axis is treated differently. In the slide, the angles are shown as approximately 116.57 degrees, 116.57 degrees, and 126.87 degrees. This projection offers a slightly more realistic 3D appearance than isometric but requires more effort to draw precisely. Trimetric projection is the most complex among the three, as all three axes have different angles and degrees of foreshortening. Trimetric projections provide the most realistic spatial representation but are rarely used in manual drafting due to their complexity.